So welcome to this class now, and as in the last class we just introduced the extraction of electrons from a metal surface. Usually it is a tungsten or the lab 6. Tungsten is used for thermoionic sources and also for the FEG, which is a field emission sources. So as last class we talked about the field emission sources. So here the advantage of field emission source is a very high brightness, which is around 10 raised to the power 13. It needs a couple of anodes which to extract the electrons from the surface, and also the energy spread is less than 0.5 electron volt, which is very low as compared to the 1 to 2 electron volt for thermoionic sources. This will have a direct consequence on the resolution on the electron microscope. Remember, we are talked about the lambda, variation of lambda in optical microscopes in light. So here that lambda is related to your it is directly related to your energy spread, correct. So here it is less than 0.5 electron volt. Okay. So now what we do is now we have generated the electrons and we have accelerated it, correct. Now these electrons actually has to be accelerated much faster with a velocity across the column, correct. For doing that we use certain amount of lenses which are called electromagnetic lenses. Okay. So and these electromagnetic lenses are very important for acceleration and also for the deflection. Okay. So the deflection of electron is very important when these electrons travel across the column. Okay. So these electromagnetic lenses in electron microscopes can be used to focus the electrons with a small probe as it is up to 1 nanometer to produce electron image of the specimen. So these focused electrons are used to image the specimen. So these electromagnetic lens, it consists of coils. So this is called a cross section of a lens. Okay. So usually the lens is a cylinder which is having a small hole at the center. Okay. And if you cross section it, then you will see this cross section as it is, and this coil consists of a large number of turns of wire, and this particular wire is made up of copper, and it is wound on a soft iron core, which is also called a pole piece. Okay. And there is a very small gap. So this is called a gap, very small gap across which you can generate the field. These are the field lines while passing the current across the copper coil. Okay. So this field is generated by the principle of electromagnetic induction, correct. So the force can be given by this particular equation. E is the charge, B is the magnetic field strength, and V is the velocity, correct. So if you zoom out this particular region, you have a magnetic field direction. These are magnetic field direction, which is not either horizontal or not either vertical, due to which it has a certain resultant components, which is called, in a vertical component is called B axial, and a radial component which is called B radial. And depending upon the electron travel trajectory or electron the movement direction, either B axial will come into play or either B radial will come into play. At certain region both comes into play, which applies a force on that particular electron depending upon the direction of the electron. Okay. So this particular force is called a Lorentz force. Okay, and this Lorentz force is created by the experience by the electron by the electric and magnetic field, and due to this Lorentz force there will be a deflection. Which is the physical basis of any electron lens. Okay, and this deflection process, while the electron travels across the column, then usually these are used to focus the electron beam. Okay, and these magnetic lenses are preferred due to the it creates a low aberrations. Now to understand it better, when you don't apply any electric field, so usually the F is a vector normal to velocity and the magnetic field, which are inclined to one another at an angle phi, which is given by this particular equation. So to understand in a simple lens system the direction of force act on a moving electron in a magnetic field, what we consider, so consider that the electron is moving in a magnetic field B. So this is your electron, it moves in a magnetic field B in this particular direction, and the force on the electron can be given by E cross B cross V, E into B cross V, and this force is as per the rule, thus this force is applied in a direction perpendicular to both direction of motion and the field, magnetic field B. Okay, so the force direction is perpendicular to the motion, the velocity direction, and also the magnetic field. So as the electron enters to the lens, entering the lens experiences a magnetic field B. So if consider the electron is lying at this position and it experiences a magnetic field B, which can be resolved into two components, B axial and B radial. Now you can see that the electron direction is downward and your B axial component is parallel to this direction. It means that it is at the angle of 180 degrees. So your sign, if you this B cross V, if you do, the force will be 0 in the axial direction, but the B radial direction is perpendicular to the movement of this particular electron. So you will have a force which is done by or which is created by the B radial direction. Okay, and due to that force the electron will deflect from that particular, in this particular direction electron will try to deflect. Okay, so initially the electron is unaffected by the B axial because it is parallel to the direction of travel, but it experiences a B radial, okay, of magnitude B radial EV, because it is 90 degrees sin 9, okay, from small, so it generates a small radial component B radial which exerts a force, and this force causes electron to travel in a helix manner. The electron will travel in a helix manner along the lens. As soon as it spirals, it has a component of velocity which is V circumference, which also we call as a V radial. So you can see that the now velocity direction is perpendicularly lateral, like along the field, but as this force is applied, the electron moves in a helix funnel and it has a velocity component which is in the mode of V circumference, and due to this V circumference B axial component will get activated also, and it will have another force which is related to B axial EV circumference in the radial direction. So, this is how you can see that as the electron moves, your force direction also changes along with the movement of that particular electron, and what will happen is this helical path gets tighter and tighter, and you will get a very sharp spot of the electron beam. Okay. So, this is how the electron beam is focused by using these electromagnetic lenses. So, the parallel beam of electrons which are entering the lenses converge to a singular point. It is similar to the lens which uses light to focus to a certain point, correct. So, in magnetic lenses these extends over a short distance along the axis. Okay. So, in thin lens we can apply for the it is similar to the thin lenses. So, your magnetic field should have a optimum value of strength and that size and shape, so that it will apply the magnetic field homogeneously across the column, across the circumference of the column. Okay. And this can be tuned by the current which is passing through the coils or the copper wires. Okay. So, the magnetic field strength and the focal length can be varied by controlling the current which is passed through these copper coils. So, this is how we achieve the focused electron beam in any microscope. Okay. So, this is different from a light microscope where you can, as the light is spread. Okay. And this magnetic field also uses to deflect the entire beam of electron. So, you can use these coils, or so there are different coils. It is not about only the function is related to the focusing of the point. Usually these electromagnetic coils can also be used to deflect the beam. Okay. And also it can be used for the scanning the beam, especially in the SEM. Now, here this is one cross section. It is a very nice image where you can see that this is your magnetic lens. Okay. This is your soft iron pole piece. These are the coils. You can see that the electron travels along this green axis and it accelerates towards along the column. Okay. And it is nothing but you are using your light, and there is a lens, there is a glass lens, and that particular is focused to that point. Okay. Now, if you assume this in an optical system, you can actually to visualize it properly, in the place of lens you can actually put these electromagnetic coils. It is exactly resembled to a lens here. What is the function? And this is how you can actually visualize in an optical system, where if you use this electromagnetic lens, you are actually doing the same thing as light focuses, and you are focusing the electron beam by using the electromagnetic lenses. Okay. This is just to visualize. Now, this is the typical electromagnetic lens. Okay. You can see that there are 2 points here. These are water cooled, because as your current passes through the copper coil, it generates a lot amount of heat, and that heat has to be extracted. So, these are always water cooled, chilled water cooled, and you can see these are the knobs where you can see that these related to your passing of the current across these copper coils, correct. So a real lens is cylindrical shape, it conceals the copper wire coils inside this. So the copper windings will be in this like this across the thickness, okay, and the two conical pole pieces beside the lens sits inside the central hole. So you will have a pole piece here, okay. So these are called pole piece, and the 3-pin electrical connections provide current to the coil to magnetize the pole pieces, and the cooling water is circulated in and out of the two holes which I shown here, the two holes of the top plate of the lens to dissipate the resistive heat generated in the coils. And this heat dissipation is very important because depending upon the heat dissipation rate, it actually controls it also affects the current in the copper coils, and hence the magnetic field which is induced in the in the column, okay. So here I am showing you just a difference between the thermoionic emission source and the field emission sources, okay. So you can see that it is just a revision that in thermoionic sources you have a heated filament which is a cathode, there is a walnut cap anode, there is a resistance heating, and the tungsten and lab 6 and large energy spread in thermoionic sources. But in Schottky emission thermal FEX, where you use the tungsten tip typically of radius of 15 nanometers, okay, these are coated with zirconium oxide, there is an anode, and you induce a very high electric field which cause emit of the energy electrons, okay. Now Fermi energy, so tungsten has a lower Fermi energy, okay, and cathode is operated at 1800 Kelvin. So here also you are increasing the temperature, but you are using the electric field, not the bias voltage, so that you are generating the you can actually extract the electrons. And brightness is 3 orders of magnitude, energy spread is around 0.6 to 0.8 electron volts. Nowadays the new advanced systems, they have a cold FEX. So these are thermal FEX where the temperature has to go up to 1800 Kelvin. Here also you are using the tungsten tip, okay, and you can see that it is on the same basic principle that you need to generate a high electric field, but here you do not have to put the cathode at a high temperature, it can be done at a room temperature. So your brightness is 3 orders of magnitude higher, and also the energy spread is much lower, that which is a 0.3 electron volt, okay. So this is just a comparison of the type of source, cathode material, and all the parameters which are very important to select for a particular type of imaging in an electron microscope. So this is your comparison with the tungsten source, thermoionic, lab 6 thermoionic, there is a short thermal FEG and the cold FEG source. The important takeaway here it is that the work function and also the operating temperature here, you can see that at a very low temperature, at a room temperature, you can get a very high brightness. And one more important term is the coherence. I will describe this coherence now. So you can see that the coherency of the beam is very important. It is the lowest in thermoionic sources, and it is the high and highest, which is very important for the high resolution imaging by using the cold field emission gun, okay. So now coming to the coherence, why coherence is important. So coherence of the electron beam is very important when you want resolution, okay. So what is coherency here? Coherency is of an electron source reflects the phase difference in the emitted beam, and thus it determines the degree of interference that can occur between the direct and the diffracted waves, okay. So if it means that the two waves are coherent when they have a constant relative phase, or when they have a 0 or constant phase difference and the same with the same frequency. Based on the coherency, there are two types of important coherence which has to be understood, which is called a spatial coherence or temporal coherence. Spatial coherence is related to position, temporal coherence is time, is related to your time. Okay. Spatial coherence, what is spatial coherence? It is nothing but all the electrons. If you have a tungsten needle, all the electrons should come from the same direction. So if an electron comes in this direction, if from this region if an electron comes in this direction, then they induce a spread or the blurred image. So your electron coming from this and coming from this will induce a blurred image. Okay. So how it comes? It comes when the electron originates from the different place of the tungsten tip. So by the time these tungsten tips are used, actually this is a destructive, correct. So this gets blunted. So if your tungsten source is blunted here, the place from here if electron is accelerated, and from here if the electron is accelerated, it will not form a perfect image, it will form a blurred image. It means that all the electrons should come from the same position. So origin of electrons on the source, different location of the source, different directions. So it creates an image at different position of the image plane. So your image plane will not change, but it creates an image at different locations. This will create a DC, which is this is the effective source size, which and it depends upon the alpha angle at the source, which is given by lambda by 2 alpha. Similarly, the temporal coherence. What is temporal coherence here? All beams should have the same speed from the source. For example, if your source, from the source, if you have one electron beam which is accelerated with 300 kV, one electron beam which is accelerated at 302 kV, what will happen is the image is formed at here, but for this 302 electron kV, the image form will be at a different plane. So you will get the blurred spot size or blurred image. They will not be focused at a same place, they will be at a different planes. So all the electrons should come out of same energy. So if it is a 300 kV, if it is a 302 kV, this particular electron will have a low speed, this particular electron will have a high speed, and you know that with this relation it will have a direct consequence on the image formation at different planes. So this we call as a temporal coherence. So here the speed of electrons from the source, so it is not from the position, from the same position, if the speed of electrons is different, then it will have this temporal coherence, and different energies at different focal points at different planes and create image at different planes, which is given by, so usually it is by lambda c Vh divided by delta E, where V is the electron velocity. Okay. So these are the two types of coherence which are very important to choose which type of source you are using in an electron microscope. Just for repeat, spatial coherence, it is related to the position, temporal coherence, it is related to the time or the same or the speed with the same energy. This is called temporal coherence. Now in the ideal electron microscopes, you will you will have a point like monochromatic source. So there will be a no chromatic operation, so the energy spread delta E is almost equal to 0. So your electron does not have any energy spread and the source is fully coherent. These are the ideal electron microscopes, which is not possible. So in the real EMs electron microscopes, depending upon the source used, thermodynamic sources or field emission sources, you will have an electron source has a finite size. There is an energy variation which is delta E, which is not 0, there is a certain energy spread, okay, and the source is partially on spatial coherence and temporal coherence beam. They have a both spatial coherence and temporal coherence issue. with these real EMs by using thermoionic sources. By using the field emission sources, you will have a very high spatial coherence which is related to your position due to very small source size. So, you will have a tip size which is around almost tip of 10 nanometers. So, it is a very strong tip, it is a very small tip, and your energy variation is with minimum as 0.3 electron volt. Okay. So, based on this, what we can if you see the any FEC source, as I told you, these are the warm and cold. Cold at room temperature, the electric field induces the electron tunneling process. Warm, the temperature has to go for 1800 Kelvin, and these are thermally activated FECs. So, here this is a typical probe size. Okay. As I told you, depending upon the coherence, spatial coherence, the actual beam diameter results from the diameter of the original beam leaving the electron gun, which is a dg, and due to the several factors related to the electromagnetic lenses and other aberrations, you will have an effect of spherical aberration which is related to ds. There is a diffraction at the aperture which is related to dd, and this depends on the current I, convergence angle alpha, brightness b, and spherical aberration coefficient Cs, and the wavelength I. So, your total d, the total beam diameter, is given by the square root of ds square, dg square, and the dd square. Okay. So, this is your final beam diameter. Okay. So, with this I will end this class now. So, we have described the importance of different types of sources which are used to extract the electrons for the imaging purpose. We also gone through the coherency and also effect on probe size, and in the next class we will just talk about how the electron and the matter interacts and what type of signals we are getting in the transmission electron microscope, and how these signals are used for specific characterization purposes. Thank you.